All right, howdy, part two. So let's see what's going on with part two. Let's say we have a material, right? A metal ball, sort of like that. Where do the charges go, right? Where do the charges go? I want to charge that up. So I'm going to, say, take a charge and put it here. I'll just add a little negative charge there. And then I put another negative charge over here. What's going to happen to them? Well, you remember that these are like charges, and this is a metal. So what does a metal mean? I guess that's the first thing. We've got a metal. And a metal is basically, I mean, this is how you can think of it, is a kind of material where electrons are free to roam, or at least some of the electrons, not all of the electrons. Most of the electrons are bound to an atom, but the rest of them are free to go from place to place if they want to, for whatever reason they want to. Mostly they'll just stay near an atom, but sometimes you have excess, so we've added a couple of excess atoms here. There's one, there's two, there's three. Or electrons, we've added excess electrons. What happens to those electrons? Well, you remember the old thing where, you know, like charges repel, they push each other apart, and unlike different charges attract. Opposite charges attract. So that's going to tell us what happens is that if you have all of these guys here, there's going to be a force on this guy, basically along the line from this charge to that charge and this charge to that charge. So he's going to get pushed off this way. Similarly, this guy is going to get pushed by this guy and that guy this way. This guy will get pushed by those other guys that way. So the charges are going to end up equally spaced along the edge. That's completely true all the time, so that if this guy is charged up, basically, then all of the charges will end up on the edge here, and they'll be equally spaced all around the border, the surface of this metal sphere. So that's where the charges go, at least in a metal sphere, and that's probably sufficient for us. We'll talk a little bit about charges and stuff like that, but the nice thing about this is in a metal, the charges are free to move around, and they move to a configuration where they're as far away from as many other excess charges as possible. Excuse me, not previously. So that's good. That tells us sort of where they go. They go to the edges. So let's say that 2. The charge on a metallic object is uniformly distributed. It means it's the same at any particular point on the surface of the sphere. Oh, getting close there. Made it. On the surface of the object. This isn't really true. If there are corners or something like that, it can make for clumping and stuff like that. So this is approximately true and good enough for us. And this is because they're all trying to get as far away as possible. And it gets a little weirder when there are places where there are surfaces that are closer to each other than other surfaces. So you have to do some, integrals and derivatives and things like that. And, it's just a little bit of math. But I think we want to avoid that kind of math. So we'll just pretend it's uniformly distributed. That's good enough for whatever we're going to do in 201. So what does this uniformly distributed mean? Well, that, again, it means it's all over the edges. So the charged surface has an average charge density we'll call that D2 because this is on the surface, so it's a two-dimensional thing. So the average charge density, D2, the little bar means average, D just means density, is equal to the total charge on the object over the surface area of the object. So this is total charge, like in the last video. Hopefully you can see that last one. And this is the surface area. I'll abbreviate that surf. Thinner pens are good, but they still have the same problem of not being able to go off infinity to infinity. All right, so this is basically what the problem will be about. Is it'll figure out the charge density given a charge on some sort of cube or some sort of sphere or something like that. So we'll just figure that out using this, right? This is what it's that's how it's related to a density, right? So you could have an average volume charge density, which would be d bar sub 3. That would be the charge over the volume. Another interesting one that we might use is B. And in B, you could say a charged wire or a charged tube. You want something very, very thin. That will be approximated by a linear charge density. And this will be interesting when we start talking about currents, because you can talk about the current being a linear charge density that's moving to the right or the left. And so basically what you do with that guy, d bar 1, is you say that there's this charge all along here, right? So we have this negative charge along here. And then anytime you take a cut of that, like this, you end up with a region right here that has the same charge density, right? The same amount of charge. So it's basically talking about that entire region right there. And that's going to have the same charge density here, so that's going to have D1 bar. Then over here it'll still have D1 bar. That's all we're going to do. We're not going to do any variations on that or try to figure out distributions. That's fun. That's a lot of fun. But we're going to be happy just saying that if we take the total charge and divide it by the length of the wire, we end up with the linear charge density of the wire. Now for a current, the linear charge density is going to be 0, but you can say that I've got the electrons, they're moving left or right or whatever direction they're moving in the circuit, in the wire, and then you have the protons, which are going to have a positive charge, and those are going to be a positive linear charge density, but they don't move, they just stay still. So the only thing that's causing the current is the electrons that are moving. Okay, so that's where we're going to use that a little bit later on, but it belongs here as well. So we might ask a question or something on a quiz or a homework assignment or something like that. So that's part 2. Again, the example will be this, getting a surface charge density, so that we can talk a little bit more concretely about part 3, which will be what happens when you take two metallic objects, touch them. So two charged metallic objects, what happens to the charge when you touch them? Think about that, all right? We'll talk to you soon. Bye now.